Hello everyone, welcome to this webinar on exploring AutoML with Amazon SageMaker Autopilot. My name is Janakiram MSV. I'm an AWS certified architect, developer, and SysOps administrator. Also a Google certified professional cloud architect, an Azure certified architect, and Kubernetes certified developer and admin. I'm pretty excited to bring you this series. If you're attending this MI2 series for the first time, let me set the context. So MI2 stands for Machine Intelligence and Modern Infrastructure. Now, these are two important trends that are currently changing the technology landscape. One is redefining the data center and the cloud, which is the modern infrastructure. And the other one is fundamentally changing the way businesses are looking at IT, which is artificial intelligence, neural networks, Internet of Things, and cognitive computing. And the most interesting thing is the convergence of these two technologies. Modern infrastructure is predominantly driven by Kubernetes, and machine intelligence is driven by a set of open source technologies like TensorFlow, PyTorch, Caffe, and so on. And there is a very strong convergence that is taking place. And there are incredible opportunities that are evolving from the convergence of machine intelligence and modern infrastructure. And my objective is to bring you some of the interesting aspects of these two tracks as a series of webinars. So every alternate week, I bring a webinar from one of these tracks. And today, obviously, I'm going to focus on the machine intelligence where I talk about AutoML delivered through Amazon SageMaker Autopilot. And like most of my webinars, this is very demo-centric. And in a couple of days, the entire source code as a part of Jupyter Notebook is going to be published at the new stack, which is my media partner. So let's get started. Now, the agenda for today's webinar is what is AutoML and how does it relate to SageMaker Autopilot? So even if you're not very familiar with machine learning, you would still find this useful because AutoML is not really meant for experienced data scientists or experienced AI engineers. It is meant for developers and business analysts who are looking at getting predictive analytics without writing a lot of code. So even if you are not very familiar with the concepts of machine learning, you will still have some takeaways from this. Then I'll touch upon the capabilities and limitations of SageMaker Autopilot. Remember, this is still in technical preview, so there are certain things that may change. Sometimes the demos may not work. That's a disclaimer, but it is fairly a mature product, and it is a very unique approach that Amazon has taken with Autopilot. So I'm going to touch upon the capabilities and limitations, followed by two extensive demos. One is using the UI to build a model through AutoML, which is Autopilot. And then I will switch gears and walk you through the Python SDK to primarily achieve the same outcome, but by writing some Python code in the Jupyter Notebook. So that's the agenda. And I hope you're able to follow my session. So before I go any further, let me bring up a quick poll. This will help me understand if the AV experience is good enough. So do let me know if you have difficulties. Okay, looks like everyone is able to follow. The AV experience is good enough. So without further ado, let's get started. So machine learning workflow is one of the most exhaustive set of steps. And this is very complex and sometimes as complex as building operating systems and building software on top of that. Machine learning and artificial intelligence are becoming a branch of computer science that is very, very deep and broad and also very complex. And this is obviously not done by an individual or one software developer, but a set of individuals or even teams work towards delivering the machine learning outcome to a business. So that includes data engineers, data scientists, data professionals, machine learning developers, DevOps professionals, MLOps professionals. So there are a lot of new roles and new jobs that are being created just to deal with the machine learning workflow. But at a high level, there are multiple steps that you're actually seeing on the screen. The first one is data acquisition, and this is identifying the sources of data. And obviously, this is not going to be one one source like a typical data warehouse or a typical database, but it is going to be acquired from multiple sources. It could come via clickstream analysis, or it could come via logs, sensor data, typical relational databases, NoSQL databases, CSV files. So it is going to be a very diverse set of data sources that are going to contribute to this. And this step will essentially ingest the data from a variety of sources, uses techniques like big data, Apache Hadoop, or ingesting that to a data lake, normalizing the data, getting it to a format where it all starts to make sense. So as you can imagine, that in itself is a pretty complex step. And once the data is acquired and normalized, ready to be explored, we move to the next step, which is data exploration. And this data exploration is a step where data scientists will analyze the data to look at the patterns, to look at the missing data, and how clean is the data to go any further. So this is where a lot of tools are being used, both open source and commercial, to figure out the quality of data, because machine learning is all about garbage in and garbage out. Now, if you feed bad data, you'll obviously get bad outcome. So it's very important to make sure that we understand the quality of data, and that's what is data exploration all about. Then they move to the data preparation phase, where data ultimately needs to be cleaned and imputed, basically making sure that it is containing enough data and a good distribution. The samples are correct, it is not biased, and it doesn't have a lot of skewed data points. So all of that is taken care with data preparation, and this is where missing values get populated, noise gets removed, and quality data comes out. And then a very important step takes place, which is feature engineering. And feature engineering in machine learning and data science is a very important step. This is where basically a lot of categorical data and a lot of data that is not in a numeric or float format gets converted into a set of real numbers or numerical values, because neural networks and machine learning, classical machine learning and modern machine learning, which is based on neural networks and artificial intelligence models, all of them expect a set of numbers. So you cannot really use data in its current form. So we have to make sure that everything is encoded in a set of numbers, either int or float, which is very, very essential. And this is where feature engineering comes in. This is where data scientists spend a lot of time making sure that all the data is normalized and converted to numerical data without losing the context and without losing the meaning. And once the feature engineering is done, then comes the model selection. So there are a bunch of algorithms, a set of algorithms that the data scientists and the ML developers need to handpick. And obviously, it's not going to be just one, but a set of algorithms that are going to be chosen based on the expected business outcome and based on the data that has evolved from feature engineering. So once the model selection is done, then the actual training process kicks in, where the cleansed, normalized, feature engineered data goes through the chosen algorithm, and it comes out with some correlations and some patterns. And then there is another important step called hyperparameter tuning, where it is further optimized. The model, which is an outcome of data plus algorithm, is further tuned to make sure that it is predicting accurate results. And this is, again, a very important step, and a lot of effort goes into turning the knobs, dragging the sliders, and making sure that the actual process is accurate and precise. Then finally, once the hyperparameter tuning is done, the model is deployed and it is ready for predictions. That's where the model gets packaged in a Docker container or gets deployed in a set of VMs behind a load balancer, and it is going to be used for inference at scale. Now, as you can notice, this is a pretty complicated workflow and a pretty complex pipeline. A lot of teams, a lot of individuals, and a lot of different skill sets get applied to deliver this entire capability and manage this entire pipeline. Now, one of the trends in the ML industry is to bypass most of these steps. So obviously we can apply meta machine learning. What I mean by that is can you apply machine learning to some of these phases to even automate the process further? What if we enable customers to bring their data in its raw form, not very clean, not very engineered or modified, but bring your raw data and then walk away with a model and figure out where you want to deploy it. So that is what is actually called as an AutoML platform. So in AutoML, we essentially bring data and walk away with the model. Behind the scenes, the platform provider will take care of all the complex stages of the pipeline. Now, you never need to worry about it. And in most of the cases, this is a black box. Today, there are many platforms that are available. For example, Google has been a pioneer in AutoML. It actually offers AutoML for vision, which is based on convolutional neural networks. It has AutoML for translation, speech, and text. It has AutoML for tables, which is tabular data meant for classification and regression. So Google is one of the key players in this space. Microsoft is also very actively investing and researching in AutoML. So they have a lot of AutoML based services, and also Azure ML supports AutoML for tabular data. And then IBM has IBM Watson Studio Auto AI, which pretty much delivers similar capabilities. And then there are companies that are exclusively focused on AutoML. For example, DataRobot is one of the companies that is actually built on top of an AutoML, where they literally enable citizen data scientists to bring the data and walk away with a model. Bottom line, AutoML bypasses a lot of complex steps involved in machine learning pipelines and exposes what is really required. That is inputting data and going away with a model that is ready for prediction. And a lot of companies today are exposing AutoML in a very opaque form. Now, what I mean by that is you really don't know what algorithm has been used, what techniques are used for data prep, what techniques are used for feature engineering, and what are the hyperparameters used for the training, and how are they tuned. None of those are basically exposed. And it obviously means it's a secret sauce, though the models are available, but they are like binary artifacts. It's like an executable that you can go away with, but you don't really know what code has been written before the binary got compiled that is ready for execution. So that's where Amazon comes in. And before I get into that, I just want to give you a big picture of where AutoML stands and how it is currently being structured and offered by the platform vendors. So machine learning in cloud basically has three layers. The first layer is the infrastructure. And infrastructure is delivered via a set of virtual machines. So where you have high power CPUs and also accelerators like NVIDIA GPUs and Google's TPUs, FPGAs, and so on. And this is basically taking over the complete control, where you SSH into the VM, you download the data set, and you basically you are at the dollar or the hash prompt, and you are the driver's seat. It's like IaaS. You basically take over the complete control, and you only have access to raw infrastructure. And DevOps guys are very essential for that delivery model of machine learning. Then, just like other delivery forms of cloud, there is platform as a service. And platform as a service abstracts away the infrastructure. You never have to SSH into a VM or directly deal with CUDA drivers or NVIDIA GPU drivers. You don't need to do any of that. You basically use PaaS by calling high-level APIs, and you only focus on training, tuning, and serving. This is like PaaS. You never deal with VMs, but you bring your code, you optimize the code for scale and performance, less latency, low latency, and then you go away with a URL. So similarly, in PaaS, you basically bring a data set, you call some APIs, and walk away with the model. And this is where data scientists are really excited, and they are very empowered because they never get to deal with the underlying infrastructure. Then there are a set of services comparable to SaaS. Now, here you actually get REST endpoints. You basically grab the API key and then make a call to perform object detection, classification, auto segmentation, and a variety of techniques without ever understanding how the platform is architected, or the high-level API is used for training, tuning, and serving. But you basically make one API call and you walk away with the output. You throw an image at Vision API and it comes back and tells you what it actually sees in that image. But AutoML is very special. It is basically an overlap between PaaS and the API, which is SaaS equivalent. So what it does is it gives best of the both worlds to the users. You can basically bring your custom data and also train the data and walk away with the model. So it is not as abstract as the services API, like the cognitive APIs, and it is not as detailed as the PaaS. It is somewhere in the middle where you get more flexibility than PaaS, but you also get a bit more control because you're able to bring custom data set and train a model based on a custom data set. So in this spectrum, obviously infrastructure gives you a lot of control and APIs and services give you a lot of ease. AutoML is somewhere in the middle where it overlaps between services and platform offerings. So that's the big picture of machine learning in the cloud, and you can actually map this to your favorite cloud platform, which could be AWS or Azure, Google Cloud, IBM, Alibaba, Huawei. All of them have a very similar set of offerings. Now, what is SageMaker Autopilot? Well, Amazon has taken a long time to come out with an AutoML offering. They are actually late in the game. AutoML was announced by Google 3 years ago. Microsoft got into the game 2 years ago, 2.5 years ago, and Amazon never had an offering. So there was a lot of pressure on AWS to come out with AutoML, but they didn't want to do what the competition is doing. So instead, they took a very unique approach, and that unique approach is making sure that the AutoML process is not a black box, but it is completely transparent and gives a lot of visibility into what is really happening within the pipeline. While the competition is exposing AutoML more like an opaque black box, Amazon has taken a very unique approach of giving you complete visibility into what kind of algorithms are being used, what kind of hyperparameter tuning is done, how is the data exploration done, how is the data prep is done. You basically get to see code for each of those steps. And experienced data scientists can intervene and take over the control and mix and match what Autopilot delivers along with their customization. For example, in other AutoML platforms, you cannot choose between multiple models. For example, you may get 95% accuracy, but the size is so huge that you cannot deploy it in an edge computing environment. Now, you cannot really do anything about it because most of the AutoML platforms give you one artifact which only focuses on accuracy. But your objective is to make sure that you get a lower latency, lower size, and moderate accuracy, because you're okay to live with it, provided it is deployed in highly constrained environments like edge computing. In other platforms, you cannot really customize the final model, and you cannot do a trade-off between size of the model, latency of the model, the accuracy and the precision. All of those are the knobs that you basically turn when you are training a model. But with AutoML, you don't have those knobs. What Amazon essentially gives you with Autopilot is a set of knobs that you can dial and control how those parameters impact your final model. So you can actually make a trade-off between the parameters that I mentioned, which is size, latency, precision, and accuracy. So you actually get to control the final model based on any of those parameters. And when you're actually running an Autopilot job, you end up seeing two Python notebooks, which I'm going to show you. One is data exploration notebook that tells you how the data has been prepped and explored, and the other one is candidate generation notebook, which will tell you how the pipelines are built, what algorithms are being used, and what hyperparameters are used in creating the entire pipeline. It makes trade-offs through notebooks. The beauty of this is it's completely open source. You can basically find out why Amazon is using a specific technique by going to the GitHub, looking at the source code, and coming back to the Jupyter notebook that the Autopilot job has actually emitted. And you can also make trade-offs by changing the code and by choosing the appropriate model depending on your use case. So obviously, this gives you a lot of choice. You can use alternative candidate models by mixing and matching some of the pipelines that SageMaker Autopilot has built. And this entire platform is accessible through UI or SDK. So UI is pretty straightforward. I really love the simplicity. It is like you bring your data set, tell where the data set is, push a button, have a coffee, or maybe few coffees, because it's going to take about 60 minutes or sometimes more depending on your data set. And then ultimately you get to sort on the models and handpick one, push a button and go into inference mode. Pretty straightforward. That is the UI. And if you don't want to do that and you want to script the whole process, you can also use SDK. So what really goes through SageMaker Autopilot and what are the features? First thing is you can specify prediction target. Now, this is again very obvious. For example, you want to predict the gold price that is highly fluctuating at this point in India. So you want to really identify that specific label. So you will actually say my target prediction is gold price, and here is the data set. The last column, which is the price, is what I want to predict. Or you want to really find out whether a customer will buy a specific product or not. So it is ultimately a buy decision. It is a yes or no. So again, the prediction target is a Y or N, and the last column typically is what is given as an input for the prediction target. It actually supports regression and classification. And what it means is it can basically perform the standard linear regression and logistic regression techniques. And it can come out with binary classification, which is either this or that, or it can even do multi-class classification, where it can come out with multiple classes that the data set can actually belong to. So this is, if you're familiar with scikit-learn, you would have already played with linear regression and logistic regression. It is very, very similar to that. The best thing is automated feature engineering. This is where a lot of effort goes in, and fortunately, Autopilot automates the whole feature engineering. And then it also selects the right algorithm and does the hyperparameter tuning. So hyperparameter optimization or tuning is a very important step that will have a huge impact on the final precision and accuracy of the model. And then all of that is actually emitted as a commented, annotated, well-described notebook, a Jupyter notebook that you can actually use to modify and customize the entire process. And of course, it is integrated with one of the new products of Amazon SageMaker called SageMaker Studio. So what really happens under the hood, behind the scenes? Well, you bring tabular data source. That is one of the key aspects. You cannot bring images, you cannot bring audio clips. You can only bring comma separated value, which is typically a tabular data source. Then you feed it to the data exploration and candidate generation job. That is the entry point to the pipeline. And then you push a button, and you can stop with the candidate notebook generation. This is an option for you where you can actually do a dry run. So you're not really getting into the training and generating the model, but you are asking SageMaker to stop by generating the candidate notebooks. Now, it will not go beyond that. So it will give you a complete visibility into how to do it without actually running the job and processing the data and creating the pipeline. And if you bypass that step, where you're generating the candidate notebooks, but also going beyond that, you can actually run multiple trials. So a trial is like, it is basically a collection of data acquisition, data prep, data cleansing, feature engineering, all these steps that I have talked about in the beginning. Basically, a trial is a collection of all those steps. So what a trial does is it basically creates a pipeline to take the same data set but apply a different transformation, that is data engineering. And based on the outcome of the transformation, it will handpick the best algorithm. For example, it could be XGBoost, it could be simple linear classifier. So based on the previous step, the outcome of the previous step, the next step is decided dynamically, and it will create multiple combinations. Typically the trial would end up coming out with 250 jobs and each job is a collection of multiple stages of a pipeline. So think of a job like a pipeline, and a job has multiple components, and each component represents a stage that I have shown in the very first slide. And then once the entire process is done, like 250 jobs are done, and then you get to sort on some of the parameters. For example, the objective could be find the most accurate one, or use F1, which is a very common technique for classification. Use one of those objectives to basically sort on the best model. You pick that best model and deploy it. And once you deploy it, it gets exposed as a REST endpoint, and you can start sending data and get predictions. So it is very well structured and very well designed AutoML platform. And Amazon is maybe the first in the category to actually come out with kind of a very transparent and a white glove service that is not hiding away the process. So some of the capabilities and limitations before I get to the demo. So it only deals with CSV data. You got to have data in Amazon S3. You cannot really bring, as I mentioned, non-tabular data. So even if you have tab delimited or colon delimited, you got to make sure it is first converted to CSV. That is the important first step. And it only supports regression related models, which means linear regression or logistic regression. You cannot really have other techniques. Maybe they will come up in the future, but as of now, tabular data can only have one of these two outcomes. So obviously regression is the best possible outcome. Well integrated with rest of SageMaker features. So SageMaker Studio is a pretty comprehensive platform that comes with a lot of developer related capabilities. Think of it like an IDE. It's like Visual Studio for ML development. It has debugger, it has model monitoring. All of that is based on Jupyter notebooks. And SageMaker Autopilot is well integrated with, for example, the model monitor, where you can actually expose a model and figure out how many requests are coming and how well your model is performing. Is there a drift? Is the model losing its accuracy over a period of time? You can monitor all of that. And that's what I mean by well integrated features with the rest of SageMaker. Ability to generate only the candidate definitions, which means, as I said, it's a dry run. It's like Terraform. If you're familiar with Terraform plan, you can actually run that before you provision all the resources. So it's like when you run the candidate definitions, you're not essentially spinning up the engines. It is a dry run, and you walk away with two notebooks that are extremely useful. Multiple configurable parameters. You got to know what you're actually doing before you touch the customized notebooks. But if you understand, and if you're an experienced data scientist, you can tinker with a lot of these parameters and turn the knobs. So it's very, very extensible and configurable. One of the things that I have noticed is, even if you come with a very small data set, it takes pretty long. And there are some high-end expectations of EC2 instances for training and inferencing. You cannot do it on T2 or T3 family. You need to have an ML M4 or M5 X large, which could be pretty expensive. And I sincerely hope Amazon does something about it and lowers the bar, at least for smaller data sets where we don't need such kind of high-end EC2 instances, which are very expensive. So those are the key capabilities and limitations. And I can't wait to show you the demo. So let me switch to the demo and walk you through the entire process. So here is the SageMaker console. Now, if you are familiar with SageMaker, nothing fancy. This is what we have been seeing for a long time, since the launch of SageMaker. But what's new is the SageMaker Studio. So once you configure SageMaker Studio, you basically associate that with an IAM role. So I created an IAM role called SM user, and what this IAM role does is it actually gives permissions to access S3 buckets, because we are dealing with data, and enables us to launch EC2 instances, because ultimately the containers that are responsible for running these algorithms and hyperparameter tuning, all of them are getting scheduled inside VMs. So you need to have access to EC2 and other services that are essential for SageMaker Studio to work. So once the user is created and an IAM role is created, you can also configure single sign-on. You can do a lot of things when you are creating the user, but once it is done, you can click on Open Studio, and this is a customized IDE for your exploration and experimentation of ML. So every customer, every user basically gets a dedicated URL and a dedicated environment built on top of Jupyter Hub. So Jupyter Hub is an open source project which is very, very popular with data scientists. It supports multiple languages, including Python, R, Julia, and a variety of other languages. So once you launch the SageMaker Studio, this is the UI. Again, if you're familiar with Jupyter Notebooks and Jupyter Hub, this is very, very similar. Now, the first thing that we're going to do is to click on this experiments tab. So the experiments are basically how you kick off the processing jobs. Now, the funny thing is, the icon that you see here reminds us of a chemistry equipment, chemistry lab devices, like those jars and those stuff with test tubes and so on. In a lot of ways, actually, experiments are like chemistry experiments. You never know which combination is going to yield the result. So that's why you need a lot of trial and error, and that's why it's actually called as an experiment. Unlike a project is a very well-defined entity that has a start and end point, and you never go back and forth, whereas an experiment is always trial and error, and you go back and forth till you are happy with the result. That's why this is actually called as an experiment. So we start an experiment. So you click on create experiment, and this is the SageMaker Autopilot experiment. So here you basically give a name, let's call it MI2 demo, and then you pass on the S3 bucket. Now, for example, in my current S3 buckets, I have one bucket that has the data set, bankmarketing.csv, for example. So I will go ahead and use that as the URL. So once I give that, it basically takes the input from the S3. Now, let me show you how this data set actually looks like. So I have downloaded a pretty large data set. It's called bankmarketing.csv, and this is available from the Open Data Hub. So it has some interesting sample data. It's actually from one of the real banks. If you read about this, there's a pretty interesting history to this data set. It is a real world data set that came from one of the banks. And what it actually finds is there are multiple columns, V1 till V16, and then there is a class. And there is also an explanation on what each of those things actually mean. So the first column is age, the next one is job, and then the marital status, and then a bunch of columns. And finally, there is a Y or N. And in our case, in our data set, it is actually represented as class. So the class 1 means essentially the customer is not going to buy an additional term deposit product from the bank. It's been already tried, and he didn't buy, so that is 1. But there are some customers where the class is 2, and what that means is this was already tried and the customer ended up buying the product. So class 2 basically means that the customer ended up buying the term deposit plan and term deposit product, and 1 means he didn't bother, he didn't buy. So that's what is the class. Now what we're actually going to do is take this data set and build a predictive model to figure out if a new customer that we're going to approach will actually buy the term deposit or not. So that's what we're trying to predict, and this is a typical binary classification or a logistic regression problem. So that's what we need to give here, right? For example, in our case, when we are creating an experiment, we need to give the attribute name. For example, we're going to call this as class, because that is the column that is responsible for the ultimate decision whether the customer has bought or not. So this is the historical data. So that's what we're going to feed. So the class, and then where do you want to store the output? What is output? Basically a set of models, right? Every candidate is going to generate a model, and we need to point SageMaker Autopilot to an S3 bucket where we are going to store the outcome and the output. Once we define that, then the next one is either leave the machine learning problem to be detected by choosing auto, or you can select binary. In our case, we are actually choosing binary because it's a class 1 or 2, which is a yes or no. If you're actually predicting a real number, then we choose linear regression. Linear regression, for example, the gold price, the petrol price, the stock price, or the company revenue forecast, all of that will come under linear regression. Multi-class classification is, you feed a number of parameters and it will end up being one of the predefined classes. So that is a multi-class classification, right? For example, you define a set of parameters and then you identify the income range of the potential customer, right? You want to bucketize them into a high potential buyer, low potential buyer, and a no prospect. So that is multi-class classification. So once you choose the type of algorithm, the machine learning problem, then you can also define the objective metric. So objective metric defines what is the outcome, right? For example, when you're choosing linear regression, the mean square error is the defining parameter which will tell you whether a model is performing well or not. So MSE is a very popular and most often used parameter or a metric to measure the precision and the accuracy of a linear regression model. If you're actually using binary classification, then you can use F1. And F1 is, again, very popular with binary classification, particularly when you have skewed data. In our case, we have a highly skewed data. There are more no's than yes. You can actually see more of ones than twos. So the best accuracy parameter or the objective metric is F1. So F1 is actually, I don't want to get into the details, but it is a harmonic average between precision and recall, and it's one of the popular techniques used in binary classification. So that's it. You basically give these inputs, tell where the data is, tell what you want to predict, right? The ultimate attribute name, and then tell where the outcome should go to. Then you may choose auto, but sometimes it makes sense to define because you'll actually save more time. In some cases, Autopilot will come back and say, hey, I'm a bit confused. Do you want to do multi-class or binary? So to avoid that step, you can actually predefine the problem type and algorithm, and then choose the metric. Again, these are very, very entry-level parameters that any ML user should know. This is not very sophisticated. All right, so once we actually do this and click on Create Experiment button, that's when the SageMaker Autopilot job kicks in, and it is going to take a pretty long time. That's the reason why I'm not doing a live demo. It will take close to 1.5 hours to basically build multiple candidates for this data set. So now what actually happens during that is this. So now I go back to my experimentations and I'll show you how this actually looks like. So now I'm describing my my entire Autopilot job. So this was done 4 days ago. Now you actually see there are multiple jobs, and if you look at the count, there are roughly 250 of them. And you actually see, if you sort on the trial name, you see that the best job is this with an objective. The F1 score is 0.79, and that is the best score available among all the candidates, which actually means that after a lot of experimentation and trials, SageMaker Autopilot has found that based on the objective metric that you define, this is the best model. So now you can actually click on Deploy Model, and this step basically exposes your model inside an EC2 instance with a well-known endpoint, and that's it. Now you can actually go live and start hitting this endpoint either in batch mode where you send a bunch of data points, or you can do it in real time where you send one data point at a time. So very straightforward. And if you actually double click on this further, for example, if you go to open in trial details, this is actually pretty interesting. Now, if you take the best candidate, and if you look at the number, right, this 230 is actually the number in the iteration, in the incremented counter. That means SageMaker found that after 229 experiments or trials, it actually found that this is the best candidate, and it stopped with that because there are some metrics, parameters that you can define a threshold, saying that once you hit like 1 hour or X number of seconds, or once you go beyond this budget, you can actually stop. You can define those thresholds. So based on those thresholds and based on the best possible optimization, it will stop. So this actually found that the 230th iteration gave us the best model. Now, if you look at this candidate, this trial, it has multiple steps. So essentially, this alone is a pipeline, right? It is one pipeline. So the first one is the data processing job. So this data processing job, if you look at the parameters, has basically taken the term deposit data set, and it ran inside an ML M5 2x large. And this is one stage, one step of the pipeline. Now, once the data has been explored and processed, then it actually came to transform. So transformation is where feature engineering gets done. And here it moved to a different instance, right? And it actually applied a different Docker image that is responsible for transforming the data. So basically prepare the data, then transform the data, and then train the data. It is not in a specific sequence, but these are the steps. Then what it actually does is it takes the fully transformed data and applies one of the algorithms. So again, this is the image. This is the Docker image, which is based on SageMaker, sklearn, AutoML, and this is available in Amazon's own container registry. So it basically it ran inside an ML M5 4x large. It attached an EBS volume of 50 GB, maybe a local disk. And then it basically took the input and omitted the output to this directory, which is mapped to the S3 bucket. And finally, this job is the hyperparameter tuning. And you see some pretty cryptic things here. So what this basically means is the final step of the pipeline was the hyperparameter tuning. And again, it ran in a dedicated EC2 instance, and this was the image used for hyperparameter tuning. And these are the parameters that were used to come out with the final recommendation. So this is the entire history, of one specific trial. Now, if you go back, you actually see there are 250 of them, which means every line item you see in this grade has pretty much gone through this phase. So you can imagine what kind of computing power and parallelization that has gone into it. That's not all. Now, the moment this gets kicked in, you'll see there are two links here: open candidate generation notebook, open data exploration notebook. Let's start with the data exploration notebook. So here you notice that this is a standard Jupyter notebook, and it tells that it has read 45,211 rows in the training data set. It has 17 columns, and the binary classification was the problem definition. There are two examples of labels, 1 and 2, right? That's what we have seen in the previous data set, right? 1 and 2. So then it basically, dumped the data. This is a limited sample of the data set. And then it has analyzed 17 input columns based on the original source. And it has moved that into feature processing pipeline for each training algorithm. So every training algorithm first gets a pre-processing stage, and based on the outcome of the pre-processing stage, an algorithm gets chosen. So that's what is actually shown here. And it also tells us if there are any techniques that were used. For example, if there is an unknown category under the categorical feature, it will figure out how to deal with it. And it will also give us some interesting stats, like, what are the unique number of entries, and if there is any string or text data, what is the count of that. So it gives us all the insight into the data set. And if you're actually noticing this, this is exactly what you do with pandas, right? If you are using pandas, before you call the train method of Keras, in Keras it is basically the in sklearn it is the fit method. In Keras, you basically use the fit again, but before you get to that point, you actually need to do a lot of pre-processing. That is what is being done here. And then it also tells us the descriptive statistics, like what is the mean, median, min, max of numerical values. So it is exactly what a data engineer would have done or a data scientist would have done with this data set before handpicking the right algorithm. So once that is done, we can also look at the candidate generation notebook. So the candidate generation notebook is a follow-up to the data exploration notebook. They are actually independent assets, but they are interlinked, as in, the data pre-processing is done in the previous notebook. It gives us a lot of insights into how the data is structured, but it doesn't really perform any real transformation. The real transformation happens here. So this auto-generated notebook tells us what are the generated candidates, and who are the selected candidates, and how the execution really took place, and how the model selection and deployment can happen. So it all starts from downloading the data set, right? And even the actual artifacts that are being generated, and you can look at the entire code generated for this. So here, this is the kind of initialization where we are saying this is where the source is, and these are the algorithms that may be used. XGBoost is one, linear learner is the other. So this is some initialization, and after that the actual pipeline becomes available. So this is the very first one. So DPP0 XGBoost is data pre-processing based on XGBoost. You'll notice that for the transformation, there is a different instance type. That's what we have seen here. And that's exactly what is being articulated in this notebook. So this is the first phase of the pipeline, ML M5 4x large. And once that is done, then you move into the next stage where you get into the algorithm. So pick up XGBoost, run it inside this. Now, this is the first candidate, where we are using a different algorithm and a different transformation. Then the second technique is DPP1, where XGBoost reminds the algorithm, but the data processing goes through a different technique. For example, here it is using robust imputer using threshold one-hot encoder. Here it is just robust imputer, and it doesn't use convert missing values to NaN. And it also uses robust PCA followed by the standard scaler. And here there is no robust PCA. So you actually notice that it is applying different techniques, and based on the technique, the actual training will be performed. So if you actually scroll down, each of these stages, for example, DPP 9 is the last one. So here it uses a very different set of transformation and a very different set of algorithm. So ultimately, this is the pipeline, and each of these definitions would result in multiple trials and multiple jobs, and that's why we see 250 of them. And ultimately, you can query who is the best, right? So, and once you find the best algorithm, you can then go ahead and deploy it. So this is the final step, where the best multi-algorithm hyperparameter optimization training job is blah. You basically grab that, and then you deploy the best pipeline. And this pipeline is what is going to be exposed as the inferencing endpoint. Now, the beauty of this is you can actually modify this at any point, right? All of this is well documented, and if you're an experienced data scientist, you precisely know how to deal with each of those steps. And these blue boxes tell you what are the available knobs: hyperparameter ranges, objective metrics, recommended static algorithm hyperparameters. So all of that is well documented, and these links actually will take you to GitHub. So all the algorithms, all the Docker images that are being used, everything is well documented and it's completely transparent. So those are the two notebooks that get generated when you run Autopilot job. So that's the first step, right? So this was with Autopilot SageMaker Studio, where you point SageMaker Autopilot to an S3 bucket, push a button, and watch the best candidate to emerge out of this. The next one is using Python SDK. So let me close all of this and open an interesting notebook. So here, I switch to my file explorer, and I will open my Python notebook. So here this is completely the scripted version of what we have seen in the previous step. And this will give you a lot of clarity on actually what goes into Autopilot. So the very first step, we deal with the Boto and SageMaker libraries. This is again available on GitHub. This is an open source library. So we grab the current region name and then we grab the session, because session is the runtime environment. So we get this, and then what it basically means is, here in S3, this will end up creating a bucket. For example, this is the bucket that was created in the previous step. So term depot, and within that there is test and train and output and so on. So that is what we have created in the very first step. So create a bucket, and then within that bucket create a key by name SageMaker / term depot. So term deposit, right? So then we go ahead and download the data set, right? So because we're actually using a Linux-based container running inside a VM, you can execute commands like wget. So I'm using wget to basically grab the marketing CSV file that is available here. You can actually do this on any machine. So this is available right here. So you can always grab the CSV file straight from this portal. So that's what I'm doing here. So I grab the CSV file from the data hub, and then I give the local path as bankmarketing.csv. So it gets downloaded here. So once the dataset is downloaded, then we do a bit of exploration. We need to do this because we want to split the train and test dataset. So this will verify that the data is indeed downloaded and it is in a clean form, and not so clean, but at least in a readable form. It's not corrupt. And then what we do is we split the data set into train and test. So 80% of the data set goes into train and 20% goes into the test. And we are using a random state of 200. And this is to make sure that every time we run this, we get a very predictable train and test data set. So the outcome of this is two different data sets, from the original pandas data frame. So now we are actually splitting that into 80% of train and 20% of test. And then what we do is we basically upload it to the S3 bucket. So this actually goes to /train and /test. So if you look at this, so this is the train data set. And if you look at this, this is the test data set. That's what we are actually doing in this step. So split the data set and upload the train and test, because we want to save 20% towards test to actually see how our model is performing. And then we define the job config. And this job config is, again, it is basically a Python data structure, nothing fancy. So you're actually saying that the max runtime per training job in seconds is 600. That means we are basically running this for 10 minutes. Each training job is going to run a max of 10 minutes. And the max AutoML job runtime is about an hour. So that's what we define here. And once we define the parameters for the job configuration, then we need to tell where the input is. So here we are actually saying that grab the data set from the S3 bucket, which is /train that we have created in the previous step. Target attribute name is class. Now this is very essential. Even in the UI, we had to mention this. And this is what is going to be the label that we're going to use for prediction. So target attribute name is class. Then where do you want to store the output? So again, we are passing the same S3 bucket, but with /output. And at this point, we are very, very similar to what we have done from the UI. Define the input, define the output, and then tell what is the problem type, binary classification, what is the objective, F1, because we are using binary classification with highly skewed data. We are again using the objective as F1. That's it. Once we define the input, output, and the job config, we are going to kick off the job. So here we call this API, create AutoML job from the SageMaker object, and we pass the job name, which is unique name that is generated based on the current timestamp. Input data config, basically telling where the S3 bucket and the data set is. Output data config, same thing on S3 bucket /output. Job config, how long should each trial run and how long each job should run. What is the objective, whether you want to do F1 or MSc and so on. And what is the problem type? Is it binary or linear or multi-class and so on? So role ARN is for SageMaker to negotiate with rest of the AWS services like S3 and EC2 and so on. That's it. Once we kick off this job, this is some basic housekeeping code, which will tell us the current status. So I run while job run status is not in failed, completed, or stopped, sleep for 30 seconds and print the status. So if you notice, there is the first step, analyzing the data. And this ran for about half an hour. Then there is a lot of time that went into feature engineering. Then after that, there is model tuning. So model tuning is also a superset of model training. So training and tuning happen hand in glove. So you actually notice that model tuning has taken place. And finally, max AutoML job runtime reached. That means because we defined 60 minutes as the max time, it stopped by then. Once that is done, I go ahead and grab the candidate definition notebook location. So I copy both of them to the local machine, to the local container. So they actually show up here in the file explorer, and I can open them in the studio. So once that is done, we have a model. So from the best candidate, we basically define what is called as a model. So model is ready for serving the prediction. So once we create the model, we need to expose that as an endpoint. So in the next step, I basically create an endpoint. So we have trained, and this has generated 250 or 200 plus candidates. And now I'm actually asking the SageMaker Autopilot to tell me the best candidate and point me to the container that is hosting the model for the best candidate. I'm grabbing that container and creating an endpoint. And this endpoint is nothing but a REST endpoint. And that basically shows up here. So if you actually see, I have an endpoint, and this endpoint is now responsible for taking the requests and serving the predictions. So that's what I'm actually creating here. So this is the endpoint creation, and now we are ready to invoke the actual prediction. So now I'm creating a line item, right? So if you notice, I have some data, but it doesn't really tell whether the final class is 1 or 2. We are omitting that and sending this data to the endpoint. And when we actually run, it comes back with 1. That means for this data points, the term deposit will not be bought. So this is live inferencing. This is real-time inferencing. Now I change to a different data point and execute the inferencing, and it comes back with 2, which means most likely this customer will buy the term deposit product. So we are actually doing live inferencing from the best candidate that was converted to a model, and from there to an endpoint. And this is an example of how we do batch transformation. So remember, we set aside the test data. Now we are actually passing this test data to the endpoint, to the model, not the endpoint, but the model. And we are saying transform this. This is going to, again, because it's a batch mode, it is going to run inside an EC2 instance, ML_M4X large, and it's going to take a while. And once it is done, it basically comes back and dumps the data in S3 bucket. So this is what happens when you actually run this job. So in progress, and then finally it gets completed. It takes about half an hour, depending on how large your test data set is. Once it is done, it basically uploads the final inferencing results to S3 bucket. And I tried printing that, and you notice that there are 1s and 2s actually telling that 9,041 rows, and for each row there has been one prediction, which is 1 or 2. 1 is no, 2 is yes. So that is basically how the entire autopilot works, both from the SDK's perspective and the UI perspective. And we are almost at the top of the hour. I want to thank our sponsors, Google Cloud, for sponsoring me with the infrastructure and all the resources. Newstack, my media partner. In a week, you'll actually see a lot of content on the same topic. I'm going to publish a step-by-step guide and a tutorial of the same demo that you have seen. And if you're watching this on YouTube, click on the description and you'll find a link to the tutorial and the GitHub link to the notebook that I have used. Foghorn, one of my clients and sponsors, an edge computing company based in Bay Area. Portworx, another sponsor and a client based out of Bay Area, a container management company. I want to thank our sponsors, and I'm pretty excited to announce my next session on modern infrastructure. This time I'm partnering with Pulumi, a Seattle-based company that is building a very unique infrastructure as code product. And we're going to show you how you can write code to target deployments across multiple platforms. So how do you do multi-cloud by writing code? This is going to be very interesting. I have Joe Duffy, the CEO of Pulumi, joining me on March 5th on the MI2 track, the infrastructure track. And this is going to be an exciting demo. So you can go ahead and sign up at mi2.live. So at this point, I want to bring up a quick poll just to get your feedback. So how relevant was the webinar? Did it really meet your expectation? Excellent. Okay, all of you said it is highly relevant. I have one final poll, which is customary. How do you rate the overall experience of attending the webinar? This includes the audio, visual, my presentation, the quality of demo, everything. Great. I'm very happy to see the outcome. I think all of you really liked this webinar and found it useful. So thanks once again. I'm committed to bring you cutting edge technologies as a part of MI2 webinar series. Stay tuned. I'm also bringing you a session on Azure ML pipelines, that is the one after infrastructure as code. So you can visit mi2.live and sign up. So thanks once again. Have a good rest of the week, and I will see you in the next webinar.